Hi, this video clip is for automatic control class. My name is Pannawit Narasetthawat. My student ID is 641054637. Let's begin with the cruise control. The car mass M is 1.3 times 1000, which is 1300 kilogram. The damping is 1.2 times 50, so it is 60 Newton second per meter. The relevant speed is 12 meters per second. I made two models, a SimScape model and a transfer function model. After that, I tested both models by giving a step input. The outputs from SimScape and transfer function were very similar, so my models seem to be corrected. And this is the result. And here I used the base cases for two gains. One is 5 and the second gain is 1 by 1.44 to get the reference speed. Next I design P controller. As you can see, for the step response for this P controller, it improved the speed a little bit but has steady state error. And for root locus, the P controller moved the pole left a little, but not much improvement. And for board diagram, it gave small gain and phase margins, so the system was not very robust. For PD controller, the step response, it made the system faster but still had some steady state error. And for the root locus, it added a 0, made the root locus move left, making the system faster. And for board diagram, the controller increased the phase margin, making the system more stable. For PI controller, the controller removed the steady state error but made the system slower. Root locus, the controller added a pole near 0, improved stability a bit. And for board diagram, the controller had better low frequency gain, but still weak at higher frequencies. The last controller is PID controller. For the step response, which is this one, the PID controller gave the base result, fast response and no steady state error. For root locus, it gave the base root locus shape. And for board diagram, the controller had the base overall margins, both gain and phase, meaning the system can handle more disturbance. In short, PID controller gave the best performance in time domain, root locus, and board diagram. It made the cruise control system fast, stable, and strong against disturbance. Part 2, motor speed. The motor parameters according to the table are inertia J value 0.9, damping 1.2, Ke value 0.8, and inductance L equals to 1. There are two models, SimScape model and a transfer function model. And I compare the outputs. This is the result. I tune the parameter of J and KT, J to be 0.3 and KT to 80 to get a better response for the requirements. Now for P controller, in step response, P controller made the model faster, but there was still some steady state error. In loot locus, it slightly shifted the poles left, and for bow diagram, the controller gave small phase margin. For PI controller, the step response, the PI controller removed the steady state error but made the response slower. In loot locus, it added a pole at the origin, which improved stability a bit. And for bow diagram, the controller improved low frequency gain, better tracking. For PID controller, in step response, PD controller. For step response, it made the system faster with a little overshoot. And in loot locus, it shifted the poles left quickly, making a faster system. And in bow diagram, the controller improved phase margin, better for fast response. PID controller for step response. PID controller was the best, fast rise time, no overshoot, and no steady state error. In loot locus, it gave a good balance, poles moved left and became more stable. And in bow diagram, the PID controller gave the highest phase and gain margins, making the model system very strong and stable. Part 3, model position. The parameters according to the table are J 1.2, BP 0.8, and KB 0.8, L 0.8. And I use the two parameters according to the site, RP to be 4 and K equals to 0.0274. A SimScape model showing model position movement and transfer function model matching the equations. And I compare both models. For the base cases of part 3, in closed loop, I put gain input 15 and gain feedback 1 by 0.36 to get the base response. Now for controllers. For P controller, the step response, the P controller improved speed but had steady state error. For loot locus, it shifted pole slightly. For bow diagram, it low phase margin. PI controller. For step response, the controller removed steady state error but slowed down rise time. In root locus, it improved system stability by adding an integrator. And in both diagram, PI controller better low frequency tracking. PD controller for stable response, it made the response faster but small steady state error remained. For in root locus, it made post move left faster. And in both diagram, it is better phase margin. For PID controller, it gave the best performance with fast rise time and no steady state error. But as you can see, the settling time for these four controllers are not according to the requirements, which is to be less than 0.1 second. For P controller, it is 9.04. For PI controller, it is 8.51. For PD controller, it is 2.22, and for PID controller, it is 10.9 seconds. In motor position control, I could not tune any controller to make the settling time less than 0.1 seconds. This is because the system has high inertia. The value is 1.2. It reacts slowly by nature. Also, the system has high electrical resistance of 4 and inductance of 0.8. It slows down the electrical dynamics. In control system designer, even when I add zeros with PDA or PID, the poles stay near the imaginary axis. That means the system cannot move fast enough. And in root locus, the branches move slowly left, but not enough to make settling time under 0.1 second. In both diagram, I also see low bandwidth, which limits the speed of response. Part 4, aircraft pitch. The parameters are A equals to 0.8, B equals to 0.8, and C equals to 1.2. Because of CTMS website error, I could not build a SimScape model, so I only used the transfer function model. Controller comparison for aircraft pitch. For step response, the P controller improved speed slightly, but steady state error remained. In root locus, small shift or pause, and in both diagram, small margins. PI controller for step response, it removed steady state error but made response slower. For in root locus, it added a pole at 0, improving stability. And in both diagram, better low frequency gain. For PD controller, it made response faster, but slightly error still existed. In root locus, it made post shift left more. And in both diagram, PI controller better low frequency gain. For PID controller, it was the best with fast rise time and no steady state error. In load locus, it showed the best pose positions for stability. And in both diagram, it gave highest margins, making the aircraft pitch control system very stable. Overall, PID controller again gave the best control. To summarize, in all four systems, cruise control, motor speed, motor position, and aircraft pitch, the PID controller gives the best results. The controller made the systems fast, stable, and good at handling disturbance. Thank you for your attention.